So today we have a session on primordial cosmology, and we're very happy to have McAllister from Cornell, who's going to start off talking about many-field inflation.
Thanks. Am I audible? Is this working all right? Yes? Okay. Thank you very much for inviting me to be here. It's always a pleasure to come to Cambridge, and this has been a great conference so far. The question I'd like to talk about today is what we can really expect to learn about fundamental physics through experimental cosmology. Now, as you know, inflationary scenarios and also alternatives to inflation are sensitive to Planck scale physics in the sense that the details of the ultraviolet completion of gravity affect the CMB observables. The basic reason for this is just that the Friedmann equation involves the Newton constant while the fluctuations are quantum mechanical, and so the Planck scale appears. And if that version of the argument is too quick, there's very extensive support for this claim in effective field theory investigations and in string theory over more than 20 years. This is a very clear point, clearly established point, and so there's a strong consensus that Planck scale physics is relevant for experimental cosmology in the sense that if you change the physics of the Planck scale, you change the observables. But that doesn't mean that it's easy to experimentally test ideas about the Planck scale, and that's what I'd like to talk about. The simple process you might think of is, well, let's propose a theory of quantum gravity. That's fine. We have one of those. And then you determine the consequences of your theory for cosmology, and you use CMB or large-scale structure, et cetera, to determine the level of evidence for the theory. The problem with this is that, in fact, there's no one prediction from the theory. Instead, you have to refine the process, propose a theory, construct an explicit cosmological model in the theory. That we've also done. Determine the consequences of the model, not of the whole theory, for cosmology, and then use CMB, et cetera, to determine the level of evidence for the model. And these last 3 points, we've had some amount of success on that in the last decade or so. The problem is it's not so clear what you learn by testing a model. In string theory, we have an innumerable collection of possible cosmological models, a landscape of vacua, and a correspondingly large number of effective field theories that could possibly support an early inflationary phase or something like it. And so what do you really learn if you rule out one model? Also, ruling out one model is not that easy. If you specify everything down to the last quantized flux and try to calculate the predictions of the model, it would require a tour de force calculation. It can be done in principle, maybe not down to the very last bit, but a rather explicit calculation can be performed, leading to a reliable prediction from one string theory model. But then what do you really learn from this? So I'd like to be a little harder on ourselves about this and not be so satisfied when we say that, well, it's predictive and I've now ruled out a model, so I've learned something. You can see the same thing from this nice picture of constraints on a very small collection of models from Planck. So the trouble with this picture is, first of all, there are no theory error bars shown. In effective field theory, there aren't any error bars. If I write down a field theory Lagrangian, I can derive the predictions, and then I can put a dot or a line or whatever else on this plot, and then I can see whether I've excluded it. But since these effective field theories are sensitive to Planck scale physics, what I really ought to do is write down an effective field theory and say, well, this is the starting point for the effective field theory, but there's a large collection of possible Planck suppressed operators that may or may not be contributing. And I need to include the possibility that those things are present. That creates a very large fuzz around each of these dots. In particular, some of these models haven't been realized in string theory. Some of them might not be realizable in string theory. So do we really want to put a dot on the plot if we're sure it can't be UV completed? The other problem is we show here a handful of models, but innumerable models exist, as already mentioned. So that doesn't mean there's no hope for using string theory. Here are just some possible ways that it's still fruitful. These are not the ways I'll be talking about today. Quantum gravity consistency requirements exclude a large number of EFT models. That improves predictivity. String theory has led us to a broader class of inflationary mechanisms in effective field theory, like DBI or monodromy. And then string theory changes our perspective on what might be natural or minimal. In a sense, parts of my talk will be inspired by this use of string theory. And we will hear or have heard some things about these approaches from prior talks. So the plan for this talk is to say a little bit more about motivation. And I'm going to try to persuade you that the existence of many moduli in a landscape of vacua requires a statistical approach. Then I'll tell you a statistical tool, random matrix theory, and explain how to use it. And the main task of the talk is to explain how to study many-field inflation using what's called Dyson-Brownian motion. This is based on some work I did with David Marsh, who's here, Enrico Peyer, and Tim Raza. It came out in July, and David already spoke about this. And then there are some talks we heard on Monday about related things. So if we want to make some sort of progress in terms of understanding the predictions of string theory and trying to constrain string theory, one obvious course for progress is to investigate examples. Now, these should be real live string theory examples resting on genuine quantum gravity calculations. In string theory, what that means is computing the effective theory in a stabilized vacuum properly, including string loop corrections, alpha prime corrections, the whole suite of quantum effects. And there has actually been some success on this in recent years, building on a decade of work by many people on flux compactifications. And here are just some examples of some of my favorite models. And Daniel and I are reviewing this, and that will appear shortly. So if you want a collection of examples, you can look in the coming review or any of the reviews that now exist, and you can see that there's an abundance of effective field theory models that emerge from string theory. And that's not the approach I'm going to take today. So I leave examples behind. The other approach, which is complementary, is to study broader and simpler classes of models that are inspired by explicit examples. In other words, generalize from the examples. Okay, it's essential if you're generalizing from some examples to make very few prior assumptions about string theory. Don't get locked into one small corner, and make those assumptions very explicit so that if you are making some restrictions, you know what they are and your readers know what they are. So what I'll do now is tell you about which prior assumptions I think we can really defend based on what we now know about string theory. So string theory, as you know, can live in many different dimensions. But the solutions that are relevant for cosmology have, of course, 4 non-compact dimensions. And the best understood solutions of string theory with 4 non-compact dimensions are geometric compactifications on 6 manifolds, compactifications on Calabi-Yau manifolds or similar spaces. So I will assume an internal space of this form. That's going to be critical and a critical underpinning for the subsequent talk. Now, supersymmetry is, of course, broken during inflation just by positive vacuum energy. It's broken at the scale h. It could very well be broken at a higher scale, at the Kaluza-Klein scale, if the compactification is not supersymmetric, or at the Planck scale. But I will assume that SUSY is not broken at a higher scale. In other words, I'm assuming that SUSY is spontaneously broken during inflation. Then the effective field theory is a supergravity theory. So to summarize the priors, all that we really need from what I've said so far, I'm going to consider supersymmetric compactifications with SUSY spontaneously broken during inflation. So it looks something like this. There are 3 large non-compact directions of space, and then a Calabi-Yau manifold. Now, the key consequence of these assumptions is the existence of moduli. Not just 1 or 2 moduli, but a large number. So by large, I mean tens or hundreds. Calabi-Yau compactifications come with tens or hundreds of geometric deformations that give rise to 4-dimensional scalar fields with gravitational strength couplings. The reason that that 100 comes in is just that's the level of richness of the topology of these spaces. That's how many. Those are typical Hodge numbers for Calabi-Yau manifolds. Now, moduli are problematic in cosmology, as you know, and a key achievement in the past decade is an understanding of classical effects like flux and also quantum effects that give mass to the moduli. These are what we call methods of moduli stabilization. But if one's a little careful about this, the masses that result from moduli stabilization are finite. So the moduli have non-zero mass, but not necessarily large mass. We'll be hearing more about this from Joe later on this morning. So let's talk about the moduli mass spectra that arise in string theory. The simplest thing you could hope for is that there are some degrees of freedom right around the Planck scale that UV complete gravity, and then there's a light inflaton. You integrate out these things up here, and then you have an effective field theory for that. That would be nice and simple. It's not what you get from string theory. For sure it's not, because string theory at least has to give you Kaluza-Klein modes at a lower scale than the Planck scale. Generally, with my assumption of a Calabi-Yau compactification or kindred compactification, you end up with massless moduli. Now, if you're able to stabilize the moduli, then these rise up to here, not all the way up to the Planck scale, but only up to, in many cases, the Hubble scale. So you end up with a bunch of fields that are around the Hubble scale, and then some more fields up here. Since these are on the Hubble scale, you can call them stabilized if you want, because they're not unstable, but they fluctuate during inflation. They can contribute to the perturbations They can contribute to the dynamics. In fact, this spectrum here is not going to give rise to inflation. There's nothing light enough. There are no inflaton-like directions. So if you also fine-tune or you impose some symmetry, then you can get to something like this, where one, or in general more than one, field will be lighter than H, but then the remainder of the dynamical fields are stranded around H. This leads to something which is a sort of a this is a quasi-single field-like scenario. So what this talk is about is trying to analyze a situation like this. What I'd like to impress upon you is that although many examples of inflation in string theory are very specific, you pick some particular corner where you understand things in great detail, and you get a very particular kind of effective action, this is much more general. This just arises from supersymmetric compactification. Okay? So what I'd like to study is an effective field theory that has a large number of hundreds of fields around the scale H. I'd like to know what's the cosmology that results from such a theory. Okay. So the way to think about such a theory is in effective field theory. So let me write an effective field theory for n scalar fields phi I. Here's a kinetic term, and then there may be a renormalizable potential, and then at the non-renormalizable level, there will be a bunch of operators that involve the fields and their derivatives with coefficients, Wilson coefficients. And the thing is, these Wilson coefficients depend on the integer inputs to the string compactification. They depend on choices of quantized flux. They depend on wrapping numbers of branes and things like this. And the number of such choices is the size of the landscape. So there are 10 to the 500 or something like this possible choices of these Wilson coefficients. So you have a vast landscape of effective field theories, and the result is that many predictions are inherently statistical. If you tell me what Calabi-Yau you'd like to study and say, predict something about inflation in this compactification, well, I can't really. It depends on what the fluxes are. It depends on all these discrete choices. So we'd still like to make progress. We'd like to understand, well, how can you make statistical predictions from this? And the core idea for this work is to use a 1 over n expansion, where n is the number of fields. So we're confronted with this problem. We have all these light fields. Let's turn that weakness into a virtue, and we'll expand in 1 over n. Why would it help to expand in 1 over n? Well, what we'll see is that at large n, central limit behavior yields universal answers to many questions, and simplicity emerges. So you get simple structured collective behavior from the not very structured motions of a lot of constituents. So the tool that I'd like to use to analyze this problem is random matrix theory. And let me give you a 1-slide review of the key, 2-slide review of some key aspects of random matrix theory. The idea in RMT is that if you have limited statistical information about the entries of some diagonalizable n by n matrix, M, then if n is large, if it's a big matrix, you can make incisive statements about the eigenvalues of the matrix, even though you don't know much about the entries. In particular, if you have an ensemble of random matrices, you can obtain the eigenvalue spectrum of a typical member of the ensemble. So you have a large collection of random matrices, and you can, with high confidence, say what the spectrum of eigenvalues will be if you draw one matrix from that ensemble. The classic example for this is the Gaussian orthogonal ensemble due to Wigner. Consider the matrix M, which is just A plus A dagger, where A is a matrix whose entries are just normally distributed random variables. Then the eigenvalue spectrum of M is given by a semicircle law in the large n limit. This comes actually from simulations from 200 by 200 matrices. You maybe can't see that there are little gaps here. This is actually a histogram underneath the curve fitted by the Wigner semicircle law. Now the great thing, which you should definitely pay attention to, is that even if this weren't Gaussian, you would still get a semicircle law. So even if you don't know what the inputs are, you may say, well, it's not, I put in something pretty strong, but it's normally distributed. Should I be that surprised that this is structured? You can take something very non-Gaussian here, and you'll still get this. And the reason is central limit behavior. The Gaussian orthogonal ensemble is the matrix equivalent of the normal distribution, and that's why it's going to play a central role in this talk. The other thing you can compute in RMT is the probability of a fluctuation from a typical configuration to an atypical one. So here's a semicircle. This is what a typical member of an ensemble of Gaussian, a member of the GOE looks like. And then it's possible, but not likely, that you could find a matrix in that ensemble, all of whose eigenvalues are positive. Turns out the spectrum of such a matrix looks like this, typically. You can compute how likely that is, and you can compute what the spectrum is when it happens. We'll need that. So here are the two key properties of RMT that we need. The first is that the eigenvalue spectrum, so just this shape, and also the probability of fluctuations of the shape, display universality. And what that means is that these observables have quantifiably limited dependence on the detailed distribution of the entries. So you don't need to know what the entries are. And don't need to know is very precise in the sense that in the large N limit, you can prove exactly how little you need to know about the entries to achieve a given accuracy in the observables. So this is a very well worked out piece of mathematical physics, although I won't be displaying any of it here. The second property, which I've also labeled 1, is strong correlations. Large fluctuations away from a typical configuration are exceptionally rare because the eigenvalues are tightly linked to each other. So in particular, the probability that you fluctuate from this configuration, where half are negative and half are positive, to a configuration where all the eigenvalues are positive, is proportional to e to the minus n squared. So fantastically unlikely. Remember, we're thinking of n of order hundreds or something for this talk. OK, so now we come to actually using this tool of random matrix theory to address this question of studying an ensemble of many-field effective theories. So why don't we just ask, what is the dynamics in a random landscape that has n fields? You could just study it directly. So Fraser and Little have done this, for example. Study a Gaussian random landscape generated in the following way schematically. Take the potential to be defined by taking its Fourier transform to have some power spectrum. So we all know a Gaussian random field from the CMB. This is just generating the potential as a Gaussian random field in n variables. This doesn't have to be scale invariant or anything like that, just some power spectrum. That generates a landscape, and then just take that thing and simulate it and see what the inflationary phenomenology is. So one should do this. The trouble is it's very, very costly at large n. The number of terms you need, just forget about simulating it, about studying dynamics, just to generate the potential. Well, let's impose a UV and an IR cutoff on K here. Then the total number of Fourier modes you need to specify this thing in some box is K max over K min to the n. So it's exponentially costly at large n just to generate one realization of a potential. And then you've got to simulate in that potential. So it's not going to happen at large n. In particular, if you wanted to study this n of 10, you can manage. But for the n of 100, 200 that's relevant in string theory, you're not going to succeed in this way. And in particular, this approach of direct simulation is not compatible with the idea of using a 1 over n expansion to simplify things. This stays in the small n regime where you don't get that simplification. So what else can you do? Well, this talk is about a way that has polynomial cost, at worst n cubed cost. And so I'll explain to you what this diagram means. The basic picture is that you could generate the whole potential, but if you're going to study inflation in this potential, you start the inflaton, I don't know, here or something, and then it moves like that, and then you're done. Well, you didn't need the potential away from where the inflaton explored. You just need the potential in the vicinity of the path that's actually explored. So this is a picture where instead of generating the whole thing, we just generate the part that we need piece by piece, patch by patch. So let me try and make that precise. Consider n fields phi 1 through phi n in a field space that's just Rn for simplicity. And we're going to specify the potential around some path gamma in a series of quadratic approximations around points p0, p1, et cetera. So let me denote the constant part of the potential at some point by v0, the first derivative by v sub a, et cetera. This idea of specifying the potential around a path, I'm going to make that work. What I need to do is tell you, if you know what the potential is at p0, how do you determine what it is at p1? Well, if you have a quadratic expansion at p0, then it's easy to get the 0th and first derivatives at p1. The 0th derivative at p1 just comes from incrementing the 0th derivative at p0 by the first derivative. Similarly, the first derivative at p1 can be obtained since you know the second derivative at p0. Oops, this is sort of obscured here. The trouble, it should say delta VAB. The thing is, how do you determine the second derivative at a new point if you know the second derivative at the first point? Well, if you specified that the second derivative at the new point is just given by the third derivative at the first point, incremented by the displacement, you're just doing a Taylor expansion. And a Taylor expansion turns out to be even worse than a Fourier expansion at large n. So it's not going to help. What we're going to do is we're going to truncate. So this would be some sort of hierarchy. You'd have to say what VABC is at P1, et cetera. You have to do an infinite order Taylor expansion. No good. What we'll do instead is we'll truncate this, and we'll propose that delta VAB here is just a stochastic variable. So the Hessian matrix, VAB, undergoes stochastic evolution from one patch to another. So the idea is you start out at one point, P0, and you know what the constant term is, you know the first derivative, and you know what the Hessian matrix is. Now you want to go to some nearby point. How do you do it? Well, through some rule that I'll tell you, you increment the Hessian by some stochastic variable. To increment the 0th and first derivative is easy. You just integrate. Now you're at P1. Now you want to go to some other point, P2. Again, increment the Hessian by some stochastic rule. And again, increment the 0th and first derivatives by integrating. And repeat. And in this way, you can generate the potential in quadratic expansion, patch by patch, along this curve, along whatever curve you like. You can't do it along a self-intersecting curve. But at large n, most curves don't self-intersect. So you can live with that. Now, the thing is, I didn't tell you what is this rule for incrementing the Hessian matrix. Why is it sensible? How can I get something useful out of it? How can we specify this process that tells you how the Hessian matrix evolves, which is basically the process that determines what kind of potential you're going to get? We're going to impose two requirements. These requirements are going to lead us to a very simple structure where we can get some nice results, some analytic results. But I want to stress that if you just drew a line here, and everything that I say in the remainder will be for some specific case, a nice specific case that'll lead to the Gaussian orthogonal ensemble. If you wanted to do numerical simulations with some other rule for a stochastic process, you could. It would be easy, just as easy as what we do. You just wouldn't have analytic results. Okay, so this is actually totally general. If you have some other kind of landscape that you like, just pick the evolution of the Hessian and generate the landscapes that way. Okay, so our two requirements. First of all, we're going to introduce some correlation length in the field space, lambda, with the idea that the potential decorrelates over distances large compared to lambda. And what we're going to do is we're going to take the collection of Hessians obtained at a set of well-separated points in the field space. So if this is the correlation length, then the Hessian here and the Hessian there and the Hessian there are independent of each other statistically. And we'll make an ensemble of matrices by drawing up all those Hessians that are far apart from each other. That gives you a collection of matrices. We're going to insist that that's some ensemble of random matrices that is statistically invariant under rotations in field space. Okay, so it's a rotationally invariant distribution. That's not building in very much. I mean, the field space was Rn. We just don't want to pick a potential on it that prefers special directions in field space. You could relax that assumption using universality, but I won't do so now. The second requirement is that the entries, that at any one point on the curve, the entries of the matrix are statistically independent. So the matrix has n times n plus 1 over 2 independent, in principle, independent entries. I'm asserting that they're statistically independent. That too can be relaxed, but I won't do so now. Now, if you take those two requirements, then you can prove those imply that the Hessian at well-separated points is actually distributed according to this one distribution I told you about, the Gaussian orthogonal ensemble. That means that the eigenvalue spectrum at well-separated points is given by a semicircle law. Okay, but this is a global thing, because I'm telling you about well-separated points. But I need to give you a stochastic process that gives you an infinitesimal increment of the Hessian matrix if you move just a little bit around the path. So what local process can achieve this globally desired result? Dyson solved this in 1962. The result is called Dyson-Brownian motion. And what he said is the rule for incrementing the Hessian, although he had a totally different motivation, is the change in the Hessian is equal to some symmetric stochastic matrix. So the independent entries of this are just some normally distributed variables, let's say. So a stochastic piece plus a deterministic piece that's proportional to the Hessian itself. Now, what is the point of this deterministic piece? The reason you need to have this is if you start with a semicircle at one place and you start adding random matrices, the spectrum will spread around and it'll develop larger and larger tails and the whole distribution will spread out. If you keep doing that over a long distance, there's no way you're going to recover a nice, tightly collimated semicircle distribution at a faraway point in the field space. You need some sort of restoring force that makes the eigenvalues stay packed together. And so the simplest restoring force you can have is a linear one. There it is. Okay? So this is the simplest kind of evolution that can give you a well-constrained distribution at widely separated points. What Brownian motion does is it relaxes some initially given spectrum. So you give me some eigenvalue spectrum. Brownian motion relaxes it to the typical configuration, to a semicircle configuration, over some time which is equal to the correlation length. This is a fictitious time. We're moving along a path. So over some distance along the path equal to the correlation length, it relaxes some sort of weird spectrum to the equilibrium, to the typical spectrum. So here's a picture. Here's the typical configuration, the semicircle. And here's some fluctuated configuration where all the eigenvalues are positive. And here what we've done, here's S, the path length along the curve. Here we started with all the eigenvalues positive and just let Dyson-Brownian motion evolve the matrix. And what you see is it tells you that the matrix wants to evolve toward the equilibrium distribution in which half the eigenvalues are positive and half are negative. And it does so over of order a correlation length. You could do this simulation for any kind of process, but for Dyson-Brownian motion, there's actually an analytic answer for what the probability distribution for the matrix is at a point S along the curve. It's given in terms of the probability of some matrix is given in terms of the matrix at the start, M0, and this parameter Q, which just measures how far you are along the curve. There's one qualitative result that I'll need before I can talk about consequences for inflation, and that is that the smallest eigenvalue gets repelled away from its initial position. So you see here that this smallest eigenvalue is very quickly pushed toward more negative values. It can't long linger around 0, even though I started it out near 0. It's expelled from the region where the other eigenvalues are. This is eigenvalue repulsion. There's an easy formula, simple formula for this. The position of the smallest eigenvalue is given by some quadratic expression in terms of this object, Q. This dashed line in blue here represents this formula. You can see that the smallest eigenvalue tracks that. So here's a picture for the only case you can illustrate, which is two-field case, of the potential over about 4 correlation lengths. It's easy to generate the potential for n of 100 or something like that, but there's not much visualization you can do even if you start slicing it. So now let's start talking about consequences for inflation from all of this scenario. So what I've described to you so far is a set of tools for generating a many-field potential. Generating it efficiently, it takes minutes to generate this thing along a path. If you want to generate it globally, you have to keep running paths along the potential and try and stitch something together, and that's very difficult. So there's some kinds of questions you just can't answer with this approach. If you want to know something about global structure of the potential, you want to know about constraints from Morse theory or something like that, this approach is not going to help, at least as currently formulated. But if you're asking local questions, questions near the inflationary path, which can include perturbations around the path, this approach can work. So what can we do with it? Well, how would inflation occur in this setting at all? Inflation doesn't happen at a generic point. Pick a typical point in a potential, a randomly chosen potential, and epsilon and eta are just not going to be small, unless you do something very fishy like making the correlation length much larger than the Planck mass, but we won't be doing that. That implies imposing a very strong shift symmetry on all the fields, which I'd prefer not to do. But you can quantify how atypical it is for epsilon and eta to be small. In particular, I told you before that the probability that all the eigenvalues are positive is e to the minus n squared. You can also compute, this is done by Pedro and Westphal recently, you can compute the probability that, well, not that the lambda min is greater than or equal to 0, but let's say that lambda min is greater than or equal to minus 1 over 100 h squared, or something like that. Some value suitable for slow roll inflation. Well, that's actually a little bit more probable than that all the eigenvalues are positive, because you're allowing a little more phase space. Not that much more probable. It's still proportional to e to the minus n squared, just with a different constant in the exponent. So there's a Gaussian suppression of the probability that any point you pick in this field space is suitable for inflation. So most points are terrible for inflation. So what are you going to do? Well, we're going to kick the can down the road. Initial conditions are a problem for the future. What I'm going to talk about in the remainder is what if you start at a point where epsilon and eta are small, what happens then? It would be very nice to know if there's some mechanism that would get you to one of those points. It would also be nice to know what sort of dynamics happens in this field space if you start at a generic point. Is there some kind of focusing that brings you to points where inflation occurs, or maybe that drives you away from them? We don't know. It would be nice to study. These tools would let you study it. But right now I'm just going to start at an extremely improbable point and see what occurs. Well, the way one often thinks about it in single field models is you take epsilon to be small and eta to be small, and you often think, well, eta, since it's a measure of the curvature, tells you how long inflation is going to last. That's not true here. And the reason is that eigenvalue repulsion very quickly increases eta. So fine-tune it as you will. Make eta as small as you like at the starting point. this eigenvalue repulsion effect means that even if you made it eta 10 to the minus 15 here, after a very short time, eta is going to be of order 1. You're not going to manage to keep eta small for long enough for it to matter for anything. In particular, one can derive a formula, I won't show it here, for the number of e-folds that arises in some model like this. It doesn't depend on eta, so you can't fine-tune the curvature small to make inflation last longer. That means that this eigenvalue repulsion effect swiftly relaxes any initial fine-tuning, and it suppresses the duration of inflation. It doesn't suppress it so it doesn't happen at all, it just makes it last less. Now there's another nice thing that that the quick evolution accomplishes, and that is it prevents you from suppressing turning. So suppose you wanted to take an in-field model and you wanted to construct a really honest-to-God single-field dynamics in that model. How would you do that? You don't want the thing to turn at all, you want it to just fall straight down one direction. The way you would do that is you would make sure that you find a starting point where the gradient and the eigenvector of the Hessian with the most tachyonic mass align. Then the steepest instability and the gradient are lined up, and you just fall right down the hill without turning. Suppose you achieve that. Well, the thing is, the eigenvalues of the eigenvectors of the Hessian change direction very rapidly. They delocalize as you evolve in this random potential. And that means that even if you've managed to align the gradient and the steepest instability at the start, that also won't last long, and you'll quickly turn. So here's an example of a simulation of an inflationary scenario with 50 fields. Here I draw the parameter eta perp, which is a measure of the degree of bending of the trajectory. So these two plots, this left one is just a zoom in of the right one. It's the same simulation, it just fits in right here. So you see that from the start, eta perp spikes up to of order 10, and then settles down as one gets into a phase of slow roll inflation. And then as inflation ends, eta perp rises and rises and rises to large values. Even though this thing is necessarily bending, you might ask, is there some single field model that captures some of the physics of this scenario? Now, obviously, you're not going to capture the physics of n-1 entropy perturbations in a single field model. But you could imagine that you could capture some aspects of the background evolution just in a single field model. So here's a model. If I introduce some rescaled variables, which are just the phi's rescaled by the correlation length, lambda, then I can write a potential in a convenient normalization with some overall scale out front. Don't worry about these. The potential has a constant term, a linear term, and a quadratic term, let's say, working in a quadratic expansion. But the curvature is going to evolve. As you move a little bit in the potential, everything's changing. And what you could do is you could say, well, I'll take this coefficient to depend on the coordinate in field space. Now, how steeply curved is the potential? Well, that's governed by the most unstable direction, by the smallest eigenvalue of the Hessian. And we know exactly how small the smallest eigenvalue of the Hessian is. I gave you a formula for it. So let me put in that formula for the smallest eigenvalue of the Hessian here, and I get some expression like this. Now, all of these things are occurring for much less than one correlation length, so I can expand this exponential inside the square root and plug it in here. And what I get is a simple model in which the potential has a constant, linear, and 5/2 piece, and nothing else, in a small phi expansion. And this is actually surprisingly successful. It reproduces our results for the duration of inflation and things like this from complete simulations. And it does so for n. We only studied n from 10 up to 100. There's no reason we couldn't do 150 or something like that, but we just stopped at 100. And for a wide range of parameters, this model gives a pretty reasonable fit. So I find it interesting that something as general as this n-field potential for arbitrary, and note there's no n here, right? It doesn't matter what n was. The single field dynamics is pretty simple. So let me conclude. I argued that string theory strongly motivates considering a landscape of many field effective field theories, and this makes a statistical approach essential. Directly constructing globally defined n-field potentials is extremely challenging, just computationally at large n. And so what we proposed is a large new class of n-field random potentials that are defined locally around a path. And these are polynomially costly. I didn't explain that. They're polynomially costly because along the path, you just have to specify the Hessian, which is order n squared degrees of freedom. And it turns out that you only need to have n points along your path in order to get a good to capture the dynamics very well. In fact, you can get by with less. So n cubed is an upper bound on how costly it is to simulate this. The key idea is that the Hessian undergoes stochastic evolution. Now, in the simple example that I gave, which you should think of as the normal distribution version of all of this general idea, I talked about Dyson Brownian motion and gave you analytic expressions. But you could do the same thing for a much broader range of ensembles. So direct simulation of n-field inflation at large n is now possible. And we're just scratching the surface of the consequences. We have actually, as you saw, very little to say about what happens. In particular, we haven't figured out anything about the perturbations just yet. What I told you about inflation near a critical point is that eigenvalue repulsion reduces the duration of inflation. So if you fine-tune to make the curvature small at the start, that doesn't affect anything later. That gets washed out. So you can try and fine-tune it, but it gets wiped away. And delocalization of the eigenvectors of the Hessian means that it's also very, very difficult to prevent turning from occurring at the initial stage. And then I showed you that this simple 5/2 model captures much of the background evolution. Now the obvious question is, well, there are two obvious questions. One obvious question is, to what extent do these Gaussian orthogonal ensemble landscapes that I've been talking about reflect what you actually get in string theory? And that's a work in progress. We have some papers on this, and we're pursuing it in various ways. Other authors are as well. I didn't say anything about that. I don't have time to tell you about it now. But the other question on the cosmology side is perturbations. It would be nice to know what the perturbations look like in an n-field model. It would be nice to know at large n, do you expect Gaussianity, adiabaticity, approximate scale invariance, or not? Are any of these things very hard to achieve at large n? I want to stress the simplicity of my prior here about string theory. I wasn't stuck in a particular class of type 2b orientifolds where we happen to know how to stabilize the moduli or something like that. All I used was compactifications that are generally like Calabi-Yao's in that they're geometrically complex. That's all. So just that prior leads you to this whole set of problems. And so it would be fascinating to understand whether the predictions of that broad class of scenarios are consistent with what we observe. And so this is a set of tools for addressing that. Thanks for your attention.
Thanks, Liam. Questions? Yeah.
Thanks, Liam. Yeah, I have two questions which worries me about this approach. Now, as you know that moduli are, they have a universal couplings. They have universal couplings to your stand model degrees of freedom, hidden degrees of freedom, to other moduli. To what extent can you ensure that all your n fields would eventually decay into, say, stand model quarks and leptons? That's the question one. And the question two is very related to this one. Suppose if they don't decay into stand model degrees of freedom, if they decay into, say, hidden degrees of freedom, then the issue is with the isocurvature perturbations, which we now know from Planck and from various other experiments that's very highly constrained. So what can we say about these two constraints?
So about the second constraint first, the question of the role of the presence of isocurvature perturbations is very important. Not only visible isocurvature, but also invisible isocurvature that converts to curvature at the time of reheating, or something like that.
May or may not, because how do you know that the hidden
That's why I
sector
say, yeah, the one or the other. Yeah.
Hidden sector may not couple to us.
Sure, it could be the one or the other. Either one of those is a problem. The reason that those are open questions here is that one has to really understand whether an adiabatic limit is reached. When you have so many fields with so many potential instabilities, you saw there's a quick trend toward instabilities developing. How are we going to ensure that that by the end of inflation, all these fields have decayed? That's an open question. Look, a possibility, which I can't now exclude, is that this prior is in serious tension with the general observations about the CMB simply because no adiabatic limit is reached, so I don't know. On the first point, I think it's clear that this proposal is a set of tools for analyzing any inflationary model, and it doesn't yet couple to the questions about the standard model. I think Joe's talk will address more directly what would happen if moduli in this sort of setting decay to visible sector degrees of freedom.
And the last question is perhaps just, no, it's a sociological question which I must raise, because the reason is, I didn't want to highlight this, but perhaps you know more than me that the first person to discuss n-field models of inflation where n tending to infinity was actually in assisted inflation.
So there's a difference with assisted inflation?
No, there's not much difference because at the time
there
were two papers. One paper was written where all the n fields were independent. There was no coupling between them. And as you confirmed that if you have n fields which are all independent, then the dynamics is a lot more smoother. But if there are couplings between the fields, then exactly what you are getting here, that even though you can fine-tune your eta and epsilon to be much, much smaller than 1, but as soon as you couple them, you tend to lose that property. And this is what is happening in the context of landscape. So it would be nice if you could,
I think that the important difference with the assisted inflation results is that when the fields are uncoupled, that it's vastly easier to analyze a system of n fields that have similar symmetry structure than it is to study a general landscape like this, which is why assisted inflation has long ago been studied for cases with many, many fields, whereas direct study in complicated landscapes like this has until recently been limited to under 10. But perhaps we should go on to other. No, I believe you've had enough questions. It's on to other people, please. No. I'm serious. It would be nice to hear from other people. I'm sure they have relevant, interesting questions.
Yeah, so actually, if you hold your mic.
Okay, so I didn't quite understand to what extent epsilon, I mean, you can actually plot epsilon along the path, and to what extent the slower parameter is much smaller than 1, and what does it depend on in this particular class?
The evolution of epsilon along the path?
Yes, exactly.
So the strange thing about the evolution of epsilon along the path is that over, I didn't highlight this, I didn't even mention it, but the one tricky business is that epsilon can start to grow over sufficiently many correlation lengths, and you leave a domain of validity of our whole construction. So over several correlation lengths, you can easily follow how epsilon evolves just by integrating up the Hessian. But as you move beyond, as you keep doing that, fluctuations tend to add up and cause the gradient to increase. So you have some nice arena in which things are happening in this general way. And in that arena, the evolution of epsilon is, I'm not sure if I'm addressing the nature of the question, but it evolves according to integrating up the curvature like this. So it doesn't run away from 0 as quickly as the curvature does, let's say. So epsilon does end up appearing in the expression for the number of v-folds. Is that the question, or?
Does the generality stay much below 1, or?
Until an inflationary period has, until partway through the inflationary period, yes. It doesn't spring away from 0 the way eta does. So that's the difference between the first and second derivatives here. Yeah.
Okay, quick question from Thomas.
So you have a certain prior that goes into the construction of your landscape, and then you're going to consider dynamics in that landscape. Am I correct that the prior that goes into the construction of your landscape implies a prior on the solutions, the dynamical solutions in those landscapes?
You mean the 6-dimensional part of the solutions? The prior that I put in had
The
to do with the
inflationary solution.
capacitor.
Assume inflation, assume fine-tuned initial conditions, but then within a certain landscape, you have a set of inflationary solutions, right? But I have the impression that the prior that goes into the construction of the landscape, the way you then solve for the dynamics in those landscapes, is implicitly using the same or a derived prior from that.
I don't think so. So the prior that I used to construct, to set the motivations for this landscape is just supersymmetric compactification.
I'm fine with the prior for the landscape.
With cosmology, not dynamics yet. You might call it a static configuration.
Yeah, I'm fine with the prior for the landscape, but
Yeah.
it's the dynamics in the way you study the dynamics in that landscape.
Well, it's because I happen to be interested in showing you an inflationary solution. If you wanted instead to ask a question like, what is the distance you have to travel in the field space between the time when the fifth derivative has one value and the time when it has some other value, just any mathematical question that you care to answer that doesn't involve inflation. Sorry, it may not have been clear. You might have thought from the way I presented it that I start here, I take a step, evolve the Friedman equations in slow roll or something like that, increment the Hessian, etc. I could do that, but I don't have to. I can just solve I don't have to solve any equations at all.
Right.
For dynamics,
Right.
I can just generate a random function. So if you like, you could think of this as a way of generating random functions, first of all. Now, what I can in addition do is study dynamics, solving the Friedman equations, not in slow roll, but exactly, step by step. So certainly all the results that I showed you about inflation had inflationary dynamics built in, but that's not a key part of the construction at all.
one very last one, and then we unfortunately have to move.
Could I ask, how restrictive do you think the assumption of randomness is?
Very good. Yeah. So this is actually a critical point. Let me actually go back to the first this example here. You can't overstate the importance of universality as a motivation for this whole approach. If universality weren't present, it would be foolish even to undertake this. So the reason can be illustrated here. So here, suppose I take the inputs. I keep the symmetry structure, M is A plus A dagger, but instead of taking these to be normally, I take them to be highly non-Gaussianly distributed. And maybe even I take correlations in the matrix, like the first row and the second row are almost the same or something like that. If I do that, at large N, I still get a semicircle law. So universality is its central limit behavior, and that means that it sort of purifies for you some impure inputs and gives you the same observables. So the question is, which observables manifest universal behavior? In RMT, two key observables are the spectral shape and the probability of fluctuations. And those are the things that were relevant in this construction. Now, random, that means, so what randomness am I talking about? I'm talking about the randomness of the Wilson coefficients here. So I don't know from string theory what the distribution of these coefficients is. I know there are many possible choices, but I have no idea whether these are not going to be Gaussian. Doesn't matter by universality. Now, there are some kinds of structures that are so important that they overwhelm the central limit behavior. And the task is to figure out what those things are. I don't know how to do that except by direct investigation, but what we've shown is that some kinds of things don't depend on inputs, and other kinds of structural things about whether your field space is compact or not do actually are strong enough that they survive. Even at large N, they matter. So we're trying to separate things into two classes, universal and non-universal.
Okay, so unfortunately I have to cut it off. We have more great speakers this morning. So let's please thank Liam again.